Take a look at the plan for the week. No lecture on Wednesday. It's a career day. And today, as Monday, I'm going to talk about Lab 4. So we already covered Lab 3 last week. So the Lab 3 itself. So the in-lab is due Friday last week. Was due Friday last week, right? So the lab itself is due Wednesday this week. So even though we don't have a lecture, but the Lab 3 is still due by the end of Wednesday. And then Thursday, we have a lab. In-lab. In-lab is pretty simple. Lab, hard. So that's why I'm going to talk about that today and give you an example or template to let you fill in with your code. Okay. If I'm doing the entire lab for myself, it's going to take hours and hours. And the thing is, if you are not able to see the demo itself, you probably don't know like what the lab instructions ask you to do. So that's why I recorded. I think it's a really good tutorial for you guys to look at as a reference, some actual reference instead of just in addition to Dr. Carlston's lab. If you click this one, if you watch the demo, you know what the results are. So now you can go back to code it up yourself. So you know what are the expectations, right? Otherwise, you probably don't know what's going on and where to get started. So I'm going to play this video really quick and show you the details of the in-lab. Hopefully that will be helpful. I think so the in-lab code is given, and whatever in the in-lab code, probably only like 10% is useful for the lab itself. That's why Lab 4 is hard. I'm giving you a template to let you get somewhere to start with. So if you look at the rest of the semester, we have Lab 5, and during the midterm exam week, which is the week 6, we don't have a lab. I want to give you more time to work on, to review the midterm exam. I'll give you some examples to work on.
Oh, I was going to ask that, if you were going to give examples.
Yeah. So I have a lecture to talk about that, right? So it's Wednesday. Wednesday will be a review for the exam, and Friday will be the exam in class. 15 minutes in class, okay? Just basic series of the. So what we have covered this week, or this semester. Logic, tools complement, all the registers, interrupts, timers, calculations, math, GPLs, and we're going to cover more about interrupts, timer 1, timer 2, timer 0, timer 1s, PWM. That's pretty much everything to be tested in the first midterm exam. And same principle, move forward. So the week for midterm exam 2, there's no lab as well. Okay, just let you guys know. And then we do the rest of the semester, cover some fancy stuff towards the end of the term. And then no lab for week 14, because no one will be able to check your labs during the Thanksgiving week. So the last lab will be Lab 11. So I was looking at Dr. Carlson's labs. So after Lab 10, I think there are like Lab 11, Lab 12. But if you keep clicking next, so actually Lab 12 or Lab 13 are not there. So even though, some of the numbers are getting skipped, you know what I mean? So even though the last lab on his website is Lab 15, but actually we don't have anything like Lab 13 or Lab 14 on his website. So there are like only 12 or 13 labs in total. And I think we have time to run through 11 of the 13 or 12 labs, which is totally fine. And the last one I picked up for you guys is accelerometer, because that one is super practical. In the future, people are building robots and all these kind of sensors, motion sensors, and this is the one you want to use. It's a low cost with a little, it's called micro mechanical systems, MEMS. It's a really popular research area that I can build micro structures with silicon and sensors into one integrated circuit chip. And that single chip can give you results of acceleration and the gyroscope, which is angle velocity as well. Really useful and practical example. So definitely I'm going to include this one into the semester as Lab 11. And that's it for the plan of the semester. So now let's come back to the Lab 4, right? I did a step-by-step for all the in-labs. I found it really useful because people are messing up with their MCC files. Is that the case for a lot of you guys, right? Okay, so by looking at the pictures, I think it's more helpful. Just follow whatever I did over here, just do the same thing. It's gonna work. And now let's look at the demo first, okay? Oh, one more thing. I think the version I used, the MPLab I used, when you generate the UART, we'll talk about UART in a bit. So UART it's called serial. It's a universal serial port. It's been called RS-232 in the past, but now it's getting very popular because it's very simple and cheap. It's usually it's being run at 9600 bit per second. And actually, when you're downloading or uploading your code through USB, it's being converted into UART and then being put into your embedded system. Okay, so at the same thing, when you are doing the communications through your embedded system to your computer, it's also running at UART. It's a UART protocol. Because this is not a Verilog or a PGA class, so we're not going to cover the details of the protocol of the UART. Usually, it's pulling down as a starting signal and then run all the digital signals through a serial port. It's just one, I think, TX and RX, 2 ports, reading and sending, transmitting. So sometimes it's getting confusing because it's not showing you the protocol, but let's just, be clear on that. It's just a serial communication. When you plug in your embedded system to your USB, it's communicating with your laptop using UART. Okay, so this is a little different version of the regular UART. It's called like EU synchronized ART. It's still very similar UART protocol. I didn't even dig into the details of this protocol, but I believe it's very similar. So it's just a UART. We are using the library to collect it, and that library and all these the files are being generated by MCC. That's everything we need to know. Okay, we are not looking into the protocols. So the protocol means you put it down, you start a signal, then you do the transmission, you acknowledge it, and then you stop it. Things like that, right? So we are not dealing with anything to that bottom level, okay? Embedded system level, just the libraries. Make it easy, okay? So you have to double click. I think it's over here after you, I know it's tiny because the lecture is recorded, so you can always come back to watch the video and look at it. I cannot zoom in this part of the menu, but you should know if you can definitely look into the details here. You generated the UART.c file through MCC, right? So here I can zoom in. You can see the initialize for the port, and the registers defines the protocol, the baud rate, and other things. No worries, I couldn't even remember what these are. I have to go back to the data sheet to look at every single register. And we didn't even use this transmitting ready and RX ready. Whenever it's done, it's gonna do something. And so we do use UART read over here because this is reading something from your board. You read it and put in the buffer into your USB port over here in your laptop. And another thing is ready. I think you are ready. Let me see what that is. Oh, here we have to replace it with integer. So the computer generated or the MCC generated file has a character type here. It's going to run, if you compile it, it's going to give you an error. So have to change it back to integer, just to let you know. Okay, no deep theory, just change it. I already showed you how to do it over here. Okay, just change it to integer type. So now let's look at the video. Wait a second. Could you hear that? Well, because it's controlled by the HDMI, so I think it's going through the speaker, but it's not really working really well. No, it's not even playing. Oh. But could you hear something on the back? Even a little bit? Okay. So what's happening is, if I just restart it, pay attention, okay? Okay, before I do anything, before I press, so you didn't see the keyboard. I actually pressed one key, okay? So before I press it, do you hear anything? No, okay? So you have to program that in your code, okay? So when I press one key, it enables it, okay? Pay attention, okay? Okay, so for the first note, I press it, it plays it for a certain duration. Okay, so the first one, the duration for the first one is longer, right? Why? Because I press it. Before I press the second one, there's probably a longer pulse over there. So what that means is, if I press it, before I press another one, the note should be kept playing. It's keep playing. Then I press another one, it plays another one. So there's no embedded system control durations or intervals between different notes, like the one you did in lab 3, right? You press one key or you press one button, it play a music for you. So this one's different. You press it, it plays one note. And you press another one, it plays another note. Okay, that's why it sounds like different durations for each note.
So you're pressing on your keyboard?
It's just one key.
Oh.
Just one key. You press it, you play one note. You press another one, yeah, keyboard, yeah, sure, that's right. So in that case, we haven't learned about how do we communicate from the laptop to the board, right? We only did push buttons, okay? You push a push button, it detects it's a zero active, it detects a zero, then it directly interfaces with your code in the microcontroller, it reads a zero, right, and do something. However, now it's from the laptop or from the computer. We haven't learned anything about it, right? That's why we have to do Lab 4. Lab 4 teaches you how to do UART. Like I said, UART is a communication between your laptop to the board, okay? And do we have to program the details about it? No. That runs through the USB, and then so the USB protocol is being converted into the UART. It's being slowed down a lot, then to UART, then communicates with. So you know what happens to UART actually? If you have program with Arduinos, it's let me just draw that to you. It's really simple, and you can do a lot of things with it. I'm just drawing the ports, okay? You have two devices. RX is the receiver, TX is the transmitter. It's basically just two digital devices. It could be a sensor, it could be an MCU. It doesn't have to be PICs, right? It can be Arduinos, can be STMs. So MCU or another device, let's just call it sensor. It's a sensor, okay? And if there's nothing to do with the laptop, we can still do UART communication. You just simply connect, just two ports actually. But definitely there's a power as well, right? And ground. If you're counting power and ground, there are totally two lines. Two lines. It's communicating with a certain digital protocol. So you connect RX to TX, TX to RX. That makes perfect sense because this one is receiving from the transmission here, right? And the other one is receiving from the transmission from the other one. So TX to RX, RX to TX. Just two ports. However, where is the TX and RX of the laptop is unclear because it's already converted. So here's the laptop, for example. I'm horrible at drawing. USB, right? USB. USB. Keyboard. And here's a PIC. Okay. Remember how many USB cables we have for the PIC microcontroller? How many USB cables you connected your between your board and the laptop? Two. So one is for what? It's called snap, right? It's a programmer. Another one is directly just a mini USB connecting to another USB port, right? Okay. One quick question before I move forward. Which cable do you think is doing that UART stuff?
The USB.
This one, right? Okay. But this is USB, this is not UART. What's happening? There's a little chip, converts it to UART. Oh, UART. And then here's a chip, here's the microcontroller itself, right? That's the microcontroller itself. So in here, what you expect after the chip, after this USB to UART converter, what do you expect? What are these two lines?
Transmit, receive.
Yeah, TXRX. Okay, here we go. TXRX. But we need to worry about whatever this chip does. No, we bought it. Someone bought it and soldered to the board. Yeah?
Yeah.
Don't have to worry about that. So that UART stuff is communicating through this line. Either RX and TX is gonna through this line. So this is just a one direction. Sometimes you can debug it, but this is just usually just uploading or downloading your code to the board, right? Through the snap. This is not UART. So sometimes you finish programming this chip, okay? You can see the instruction tells you to unplug the snap, but are still doing communication with PuTTY. So, oh yeah, PuTTY. PuTTY is UART. Okay? We did this, right? In the first lab, remember? There's a little interface. Okay? And it's asking to choose a COM port. Oh, COM port. So that COM port is a UART port. For example, COM4. If you keep this cable connected, you should be able to do all these PuTTY transmission. I can see data being sent to the PuTTY interface, or you can type something in the interface and send it to the board. You don't need this one. Okay? Right. Now let's come back to the code. In lab code, no secret. If it's a lab code, I'm gonna delete something for you, okay? No secret here. Let's take a look at it. Okay, so you already watched the demo, right? You know what's going on. You press one key. Oh, so the demo video is the in-lab code. Actually, you don't have to program it by yourself. Okay? You press it, it plays a note, and keeps playing it until you press another one. It's going to change to a different note, change to the next note. That's what you are going to do for the in-lab code. And let's see if this one is going to do that job for you. Okay, so the first one, some printing art in the serial port. You actually don't have to worry about it because they're just all printing, but nothing else. Okay, it makes the code very long. Just scare you, nothing else. All right. What about this? Okay, UART, EUSR. Let's just call it UART. Okay, don't make it complicated. So the UART read function is one of the UART function being created by MCC. Okay, you can create it yourself easily just by following the instruction on my website. So this one read the data from the port and return it to a variable. And if you assign it to CMD, which is a variable you have over here, it's going to hold whatever being read by this one. So what is being read now? Look at the function here. Oh, so this first, UART data ready. Yeah, when I taught IPGA, and we actually manually programmed every single detail about UART ourselves. If you go to my website, go to CE433, I think that's that class. I think towards the end of the semester, we have a lab back in Fortis College. So we program every single detail about it. So whenever this one is being, there's a little buffer actually in the computer. So whenever the buffer getting filled up with the data, it turns on the flag. But we are not dealing with the bottom level details, okay? No worry. So whenever it turns on that flag, it actually makes this one true, okay? it looks like it's a condition in the if statement, right? But there's no condition over there. So it must be a Boolean type, the bool type. So when this is true, okay, means there's something being received, right? Something being received. It's able to sense it. Why? Because there's a flag being turned on. But we're not doing any flags over here. It's a C level. It's upper level, not Verilog level. Verilog level, you have to do every single flag. Here, upper level, whenever this is true, just put a condition here, okay? So whenever this is true, something is received, jump into the if statement and read it. Makes sense, right? Something received, read it. You read it, it's being saved into a variable, okay? And what that is, okay, here. What is it? Yeah, something you pressed. What is the code of the key on the keyboard? No, I mean in general. So what's actually being sent from the computer to the board? 16 bits, 2 or 8 bits? What kind of code?
ASCII.
ASCII code. Remember the keyboard I showed you? Every key has a byte, which is ASCII code of each key, right? So press it, there will be a 8 bits or a byte being saved in the buffer, waited to be sent, and then every single clock will send every single bit through the UART port, which is the serial communication port over here. We are not dealing with the protocol, the details, it's okay. So we know it will be sent. It will be handled by the computer, okay, the hardware. No worries about the details. So you press it, it will be put into the switch, and depending on which has been pressed, it will print something in the serial, okay? So now let's moving forward. So these are just the different keys being pressed. So remember before I press anything, it was silent, right? Nothing is being played. So until I pressed a thing, it played a note. So that key was actually N, lowercase n. That was the first one I played. Okay. And I press N first. It sent a true to play note. I'm going to show you why in a bit. That's the only thing it does after I press N, just to turn on this flag, but nothing else. The printing function just showing you something in the serial monitor, okay, but nothing else. So then I start pressing I each time. I increment the index in this list, which is the sum, right? The sum. Where is it? I think I put it somewhere else down here. Yeah, here's the sum. All right, another important concept to introduce. So remember last time when we are dealing with timers. So when the timer overflows, what the embedded system does, what PIC does, yeah, just turn on the flag. That's it, right? So now we are using another functionality of the embedded system, which is called interrupt. So interrupt is a super powerful tool that I can use because you can have nasty interrupts in the future, but usually no more than like 5 or 4 or 5 because the simple microcontroller cannot handle that many. However, operating system can. That's why, when I'm using my laptop, I can play a YouTube video, but I'll also use my keyboard and doing programming and use my mouse as well, because the operating system can handle like hundreds of interrupts at the same time. So, however, for the very simple microcontroller, I think we are just dealing with like 2 as a maximum for this semester. So for the first one, this is it's called an interrupt routine. That's why it's called ISR. Something will be on the exam, keep in mind. So ISR stands for what? Interrupt service routine. So instead of just like when we use the timer for lab 3, instead of just to turn on the flag, when the timer overflows, we had to write a program to handle that, right? Remember, when the timer is up, we have to write like toggle something and a while loop and toggle something, right? We have to handle it manually. So now the interrupted routine is a function. Whenever the timer is up, it's going to directly jump into this function and do whatever it does. Okay? So this will be independent to everything, every program in the main function. Think about it. It's just a new concept we have ever learned, all right? What's happening is you have your main loop, right? Let me just show you on the paper. How many of you have used the interrupt in the past? Several of you guys? Okay, cool. That's your main function, right? There might be a infinite loop somewhere, like for, like that, right? Going on. So if you don't have any interrupts, nothing can break it. Is that true? It's going to keep running inside. So your microcontroller may only have one loop, cannot respond to anything else happening outside of the world. So if you have an interrupt, no matter what is happening here, it's going to interrupt it here, or here, doesn't matter. Okay? You can set up a timer. You can use a timer to do an interrupt. You can use an external trigger to do the interrupt. For example, someone press a key. It senses that key from that digital pin, the GPIO, and triggers the interrupt to do your interrupt routine, to do a function, specific function in the program. But here we are using a timer, 0 and 1 interrupts. So in your MCC, when you are setting up the MCC, you want to check that box to enable timer interrupts. So what's the difference between timer interrupts and just regular timer? What's the difference? Just compare. Now whenever timer's up, what's gonna happen? Remember? TMR1, TMR0 for example. Bits dot what? Yeah. So this will become 1, right? Whenever timer's up, this becomes 1. So you have to, before you have the interrupt routine, service routine, whenever this is 1, you have to write a program and manually handle it. But now, it's going to directly jump to that interrupt routine to do all the job over there in the function. Now let's come back here and take a look at it. What's happening? So concept-wise, it's really simple, right? This function, no matter where the program is at, where the program pointer is pointing at, taking out every single program through the program memory and putting it to the CPU to do the calculations. That's how the computer works. But no matter where the pointer is at, when the timer is up, it's going to jump into here and do the job. Okay? Now, see here, this is nothing fancy. Here's the half period. It's a list of all the notes. Okay? And let's talk about this later in a bit. So here's how this timer plays the music, plays the notes. So we have done this in lab 3, right? You write a certain number into your timer, so it's gonna generate a certain delay to create that note or scale. That's how we do it, right? So this is actually the code that plays the note. All right. So now you get confused. Timer 1 interrupts, assuming that at the very beginning timer 1 has 0 inside. So whenever after how long it's going to trigger, the timer is going to be the flag will be 1. Remember from lab 3?
2 to 16.
Yeah. But what's the value? Remember we used 4.1 milliseconds, right? Okay. So 4.1 milliseconds, it jumps to here. So what's the flag? Flag becomes 1, but whenever you get into this one, it will clear it. You got a 0 for that flag. Okay, so these lines are super fast. They are microsecond level. This is important to know, okay? It's not taking long. Because taking every instruction and run it usually only takes like several microseconds. So you can imagine that what the way the code is running is it's running the main file, okay? Running the main C file. Interrupt. Jump to the interrupt routine. Okay? How long it takes to jump into the interrupt routine every time. If the timer 1 was holding a 0 at the very beginning. Right? Do it. Then come back to the main. And then keep doing for the following ones. After a while, flag is 1, detect the interrupts, go to the interrupt routine again, run it. Okay? How long it takes? 4.1 milliseconds. Does that make sense? So the main file is running, okay, can run several times depending on what you have in the main file. Okay? So every 4.1 milliseconds, it jumps to the interrupt routine and run whatever inside. However, since we know that the timer 1 has been used, you write something to timer 1 has been used to play the note. Am I losing anybody? I'm losing a lot of you guys, I know. This is recorded, it can always come back. So only makes sense after you play you program and download to the board and modify it, then look at the results. Okay. I know when I explain it doesn't make too much sense, but hopefully will help a little bit. It's better than nothing. Okay?
So it's not necessary then to have a flag in the interrupt. You just need one interrupt that's like in place of the flag.
Not necessary to what? The first half?
So like the timer 0 bits
Yeah.
like that in the argument code in there.
Yeah.
You don't necessarily need it in place of what interrupt. Is what I'm getting, right?
I'm still not getting that. Can I say it again? Just one more time.
I mean,
Not necessary to have the interrupts to be there, or
we'll know like for the like in place of the flag of like the code for the flag, just having interrupts instead is not what like I'm getting.
yeah, it's just more powerful.
Okay.
Yeah. Yeah, you can. We will see. After you see more examples, you'll find out. It's just a more powerful tool to use instead of just using. That's right. So whenever the timer is up, it's gonna trigger interrupt for sure. Keep in mind.
Okay.
It's gonna turn on the flag. Whenever the flag is on, it will definitely get into the interrupt service routine. Okay. So if we come back here. That's why I want to explain this part because it's getting confusing, right? So every 4.1 milliseconds, it triggers this guy, okay? It's gonna run this part, the top of it, really quickly. So what's happening is it triggers interrupt. Come to the timer right. Start writing that starting value into the timer register, okay? That takes a while to run. However, it's conflicting with the interrupt, right? What's happening? What's really happening? You got two timer 1, right? Timer 1 for the interrupt routine, it triggers the interrupt, and then you get another timer 1. You are writing a new value to it to wait for the flag to be turned on again. Is it still serving your purpose to play the note? And how?
You just have less of the clock registers.
Yeah.
And it goes.
Yeah, but does that matter? Because it takes 4 milliseconds, right? To get into here. I mean, how can you generate different notes? How that works?
Well, since you're writing to timer 1, aren't you like changing the length of time the timer 1 will take to get to the interrupt?
Exactly. Yeah. Remember last time when we were talking about the different notes, right? So every note has a different sound because they have a different frequency. Remember? For example, this is C4. I just keep making the same example. C4, like this. So in that case, B4 will be Like this or this? B4, which one? So B4 is lower pitch, right?
Lower pitch would be.
Yeah, lower frequency. Got it? So different notes will give you a different frequency, okay? So how do we flip it? With a timer, right? When timer is up, we toggle it. Timer is up, we toggle it. Make sense?
Yep.
That's how we use timer to making different sound. All right. Now let's come back to this one, interrupt routine. Now this guy, 4.1 milliseconds, get into interrupt routine. The way that it can generate different sound is, I told you, the top of the code will run really quickly. Okay, you can ignore it. After it get into here, it writes a new value to it.
Which you're talking about.
We'll make it shorter. So next time, are you still have to wait for 4.1 milliseconds to get into it?
No.
Why?
Because you're
The flag is on sooner or later.
sooner.
Yeah. Does that make sense?
Yep.
Okay? So what's happening is the first time it takes 4 milliseconds for sure, right? Before you get into it. You are not ready into timer 1 with a new value. So it waits for 4.1 milliseconds, get into it, got a new value. So it runs faster depending on your node. So it's gonna be a varying duration. What's that?
Also, by modulating that timer 1, you're modulating the frequency of
Yes.
the sound and thus what tone it makes.
Yes. And since it's just one timer, the same timer, still timer 1, so whenever this timer is up, what's gonna happen? Flag is on. So when the flag is on, what's gonna happen? Interrupt routine. Didn't change anything. Still playing the same note. The note you desired to play. Okay? That's everything about InLab. Easy? Easy peasy, lemon squeezy. Let's come back to the Word file. I was why? Boring? All right. One thing you need to know. I think I have to cover the lab 4 on Friday probably because today we can only do in lab. Okay. How does your code know which one is a routine? Which one is a routine? Every time you change the name, you can call it my timer 1 ISR. You can call it blaster timer 1 ISR, whatever. Okay. So, how does the program know? See, here's a function. The function is not changing. The function is not changing. This is generated by MCC. I didn't write it. I didn't know how to write it. MCC generated, I modify it. Okay? I'm not a god, knows everything. No, I copied. All right. So how do you find the details? Control click. Control click.
That's news.
All right, control click. Get into the details. But now I want to let you guys take a look at interrupt manager first. These are the all MCC generated files. Okay? Now, there are questions in lab 4. These answers a lot of questions. Pay attention, okay? Is there a quiz today? No. What's that?
Is this what we should use to figure out like the timer overflow flags and stuff for some homework this Friday?
Homework 4?
The homework 3.
Homework 4, I think, right? Homework 3. Homework.
Yeah.
Yeah, no matter, so whatever I post on my website and also Canvas for the lecture, right? So that one, I think, just watch the lecture. I think probably we're not here on Friday. So the lecture on Friday, I covered all the details about how to calculate the timers. So watch that lecture and look at the notes. You should be fine for that one. So that one will prepare you for lab 4. Okay. That's why I will try to scare you with the quiz on Friday because that's so important. I don't know how many times I can do this for the semester. Maybe twice or 3 times. I'll change it to another way, like you couldn't figure out. But anyway, we'll do a real quiz next week. So interrupt manager.c. Get into the .c file. click it, it's in the menu, okay? Not somewhere else. Okay, see here. Underscore, double underscore interrupt. What that means? That's the real interrupt handler. What does that mean? Interrupt handler, so whenever interrupts happens, it get into there. Not your my or Blaster's ISR interrupt ISR, okay? It get into here. We'll see, okay? And then what this does, it enables interrupt, okay? And definitely because the flag will be 1, right? So if it's enabled, if it's 1, you run this guy. That's the real interrupt service routine. It's not being changed. It has to be TMR1 underscore ISR. That's why it allows you to change your interrupt routine name, because every time it's going to point to this real interrupt routine. I'm going to show you really quick. Okay, click it, control click, get into here. Important. When we are looking at the MC file, the main file, okay, the main file. All right, interrupt flag becomes 1, get into it. Oh, I didn't even clear it. Did I clear it? Did I clear a flag? I didn't clear a flag, did I? I didn't. However, this is a real interrupt service routine. Get into it. Is it getting cleared? Yes. You give a name to your interrupt routine, the Blaster one, my one, whatever. That one is just a pointer, okay? It's gonna point to that TMR1 underscore ISR always. You cannot change it. It's a keyword. It'll always get into here and getting cleared. So you'll be fine. This is one of the questions in the in-lab, okay? And get into it, write a timer interval. Oh, I don't even have a starting value for it. Where do I see it? Do I find it? Go to timer 1, initialize. It's getting initialized. Zeros. So a quick quiz question. Oh, it's not zeros even. Oh, it's generating a random value over there by MCC. Doesn't matter because it's just the very first cycle, right? Do you really care about that? You couldn't even identify it when you are listening to the speaker. Okay? I think put a 0, 0 is fine. So I think this one will give you a starting value for the timer 1 to interrupt at the very first cycle. You don't really have to worry about it. I mean, can you really figure out 4.1 milliseconds versus 5 milliseconds for the very beginning? You turn it on. You are trying to count. Oh, you are not like starting the first cycle at the 5th millisecond. Nobody can tell that, right? You turn it on, it just do whatever it does. So the initial values doesn't really matter because it's being overwritten by your interrupt routine. Okay. But is it being initialized? Yes. See, timer interval, right? No, timer 1 reload value, right? So it's being initialized. Where this is being initialized? The main file. System initialized, yes. Okay, thanks to lab 1, lab 2, whatever, lab 3, I think. Right? Timer 1 initialize. On the top of the main C file. It was done before you can realize whatever happened, okay? Initial value was written into it. So if you go to timer 1 interrupt routine, this guy does have something. All right? It's not going to report errors because it does have something from where? Timer 1 initialize. Make sense? Am I losing everybody back there? Frustrating? It's okay. Just don't give up, okay? So when you program it, Even though the first C program you write could be hundreds of errors, it's okay. Schedule appointment with me or the TA. Sit with me, spend like 2 hours debugging every single line with you, which is okay. I did it with Trevor and someone else already. And I want to do it with more students if you want to come and visit. I know a lot of you are struggling a little bit, okay? Come to visit. That's the way to learn it.
For your office hours that you have from 8 to 9:30, are you just in there, or do you have to schedule it if you want to go in there?
I will be there.
You're just gonna be there, gotcha.
Yeah. Okay. I just had how many? I think no more than like 4 or 5 students. I think I sit with them, figure out a lot of issues. So don't worry about me. I have solutions. I will figure things out eventually. All right. Interrupt handler. You get into the interrupt service routine. You'll find the interrupt handler. Get into it. So here's the interrupt handler, right? In the timer file, it's a pointer. And you'll see in the main file, you'll put your function into it. That's how all the handlers are being passed. For my timer one ISR, eventually get down to timer one _ ISR.
So it's just an alias?
Yeah, just a name. So you can keep clicking to track down to the bottom. Okay? Anything else? This one. Testing like analog circuits. So the speaker has if you go to its website, you can see a diagram, shows the frequency versus the dB, the sound. Okay, that's a speaker. So that's you can search for. I already showed you on my website.
So it's good at certain notes and not so good at other notes? Is that what that means?
That's right, yeah. For certain frequency, it has a different sound, right? A dB or value.
So we will be using your code for the in-lab, but will we be using any portion of that for the lab?
Yes, 10%, like what I said. That's why lab 4 is hard. So I think because we are doing a Thursday is the lab, right? So the lab itself is not due until what? Next Wednesday, right? Wednesday night, midnight. So I will be able to cover a lot of things on Friday and Monday. So no worries. Today we don't have time to go get into the lab code, but I will show you the template on Friday and Monday. So make sure you guys are fine. So this one will ask you about, and that's a speaker. That's a speaker. It's an audio amplifier. So if you look at audio amplifier, that's a pin 4, right? So pin 4 has an input. So input goes in. You get a cap. That's a high pass filter. High pass filter. That's the only thing you need to know, I think. So the DC offset is getting removed. And that's the schematic of the audio amplifier. If you go to the website, you'll be able to see the schematic. What's really happening here is on the circuit, on the PCB, you'll see on the right-hand side of the layout, there's a little jumping header that if you plug in the header, it's shorting here to here. Okay? This is the audio amplifier. This is the audio amplifier. This is another high-pass filter outside of the audio amplifier. And this is a low-pass filter, and that's the output. That's the input. Okay. These are, if you see, they are same name, so it means they are electrically shorted. This is the jumper. Okay. I'm gonna give me one more second. Go to the layout. See here, that's the jumper on the schematic. We'll put the low-pass filter output to the amplifier's input. Make sense? Come back here to the schematic one more time. Here's the jumper. Okay, hopefully we can cover more on, not Wednesday, but during the lab, okay? We'll see you on Thursday.